So today we're going to do stuff a little bit different. We're actually going to start off with doing a proof, then cover the objective for the day, and then move on to some definitions and examples. So let's go ahead and start with our proof. So what we have here on the right is an isosceles triangle, and what's given is that line segments AB and AC are congruent to each other, which is what makes this an isosceles triangle. And we're trying to prove that angle B is congruent to angle C. So what I'm going to do here is actually create two different triangles. So I'm drawing a vertical line going from vertex A down to the midpoint of BC. We're just going to call that point X. And by doing that, that would make BX and CX congruent to each other. And then the line we drew is congruent to itself. And so what we can do is say that ABX, that triangle, is congruent to ACX. And that's by side-side-side congruence. And because of that, then we can use the corresponding parts of congruent triangles to show that angle B is congruent to angle C. So I'm going to use a flowchart as the method to prove this. And then I'm going to show you the two-column proof also for comparison. But let's start with what we are trying to prove. So angle B is congruent to angle C is what we're trying to prove. And we know that we're going to use the corresponding parts of congruent triangles are congruent to prove that those angles are congruent to each other. So in order to do that, we need to prove that triangle ABX is congruent to triangle ACX. So adding that to my flowchart. And the reason for that we're going to show is the side-side-side congruence. So I'm going to draw three more ovals because I need to prove each, there's three corresponding sides between these two triangles. I'm going to start with the easy one first. So let's say that AB is congruent to AC, and that's just given to us. And then let's show that AX is congruent to itself, and that's because of the reflexive property of congruence. So the third side we're trying to prove is that BX is congruent to CX. So the very first thing we did was put down the midpoint X between B and C. And our reason for that is that there's always one unique midpoint in a line segment. So the next thing we did was draw the line AX. And the reason for that one is that there's exactly one line segment connecting 2 points. So now we've proven that BX is congruent to CX because of the definition of midpoint. So we have now shown that angle B is congruent to angle C in an isosceles triangle. So here's the same proof, but written as a two-column proof instead of a flowchart proof. So you can pause it here if you'd like to take these notes. So the objective today is I can prove theorems and apply properties of isosceles and equilateral triangles. So in section 4-2, we saw that isosceles triangle has at least two congruent sides, and an equilateral triangle has all three sides congruent. So now let's take a closer look at the isosceles triangle. So let's first review some vocabulary in relation to the isosceles triangle. So this would be the vertex angle of the isosceles triangle. then there'll be two base angles. And then the sides that are congruent are considered the legs of the isosceles triangle. Then the other side is considered the base. Now I'll show the same thing using words. So the vertex angle is the angle between the legs. Then the base is the side opposite the vertex angle. Then the two base angles are the angles that have the base as a side. Also think about it as the angles that are opposite the legs. Okay, so now let's take notes on two different theorems. The first one is the isosceles triangle theorem. And that says if two sides of a triangle are congruent, then the angles opposite the sides are congruent. So the next theorem is the converse of the isosceles triangle theorem. And that says if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So really the same thing, but switching the word sides and angles. So in this case, AB is congruent to AC because angle B is congruent to angle C. Now we're going to apply the properties of isosceles triangles. So in this example, we're trying to find the measure of angle H. And we know that H and G have to be congruent to each other because of the isosceles triangle theorem. So we're going to start off by saying the measure of angle F plus measure of angle G plus the measure of angle H has to equal 180 degrees. That is because of the triangle sum theorem. Then what I want to do is say that, well, measure G has to equal the measure of angle H. That's because of the isosceles triangle theorem. Then substituting and simplifying, I'm going to put 48 in for measure of angle F, and so then that added to 2 times the measure of angle H has to equal 180 degrees. So now we're solving for the measure of angle H. So subtract 48 from both sides. I get 2 times the measure of angle H. And that equals 132. Then just divide both sides by 2. So the measure of angle H equals 66 degrees. And it's always a good idea to check your work. So I'm just going to put 66 into where angle G and angle H would be. Make sure all the angles add up to 180 degrees. And yes, they do. So that means our measure of angle H equals 66 degrees is correct. Okay, let's look at the next one. So the measure of angle N is equal to the measure of angle P. And we know that because of the isosceles triangle theorem. Therefore, we're going to set those expressions equal to each other and then solve for y. So we solved that and got y is equal to 8. But we have to find the measure of angle N. So I'm just going to plug that back into the expression for angle N, which is 6y. So it'll just be 6 times 8, or 48. So the measure of angle N is 48 degrees. And I want to check that and make sure that both those angles are 48 degrees, or that they're equal to each other. So to make sure that angle P is equal to 48, putting an 8 in there, so 8 times 8 minus 16. And the left side will simplify down to 48. So our measure of angle N of 48 is correct. So we looked a lot at isosceles triangles. Now we're going to take a closer look at equilateral triangles and the corollaries associated with them. So the first one is, if a triangle is equilateral, then it is equiangular. So basically equilateral triangles have all the angles inside of them congruent to each other. We can also say that if a triangle has all the angles congruent to each other, then all the sides are congruent to each other. So let's take a closer look at the equilateral triangle and its angles. So they're all the same, so I'm just going to call all the angles A. And we know that all the angles in a triangle need to add up to 180 degrees. So I'm going to say that 3 times A has to equal 180. And what I'm going to do here is solve for A, and that will give me the measure of each angle inside of an equiangular triangle, which is also an equilateral triangle. So each interior angle of an equilateral triangle will always be equal to 60 degrees. Now let's look at applying the properties of equilateral triangles to a situation. So since this is an equilateral triangle, we know that all the angles are congruent to each other. So I'm just going to mark that on here. We can use that to help us solve for x. So one way to do that is to recall that all the angles need to add up to 180 degrees. So I'm just going to write down 3x plus 15 plus 3x plus 15 plus 3x plus 15. And those all together have to equal 180. And then from there we could solve for x. But I think an easier way to do it is to recall that each angle is 60 degrees. And we can just say 3x plus 15 is equal to 60 and just solve for that. So let's subtract 15 from both sides and get 3x equals 45. Then divide both sides by 3 and then get x is equal to 15. Okay, and then I want to check this by plugging 15 back into the original expression for x and make sure I do get 60 degrees for the angle. And sure enough, when I put it in, the left side will simplify to 60, so we know that we got the correct answer. All right, so I'm really excited about this next proof. So this one here, we are given that ABC, this big triangle here, is an isosceles right triangle, just like it's drawn. And what we're trying to prove is that when you take this midpoint here and create this line segment BX, it creates a new smaller isosceles triangle of AXB. All right, so let's go ahead and prove that that is the case. So I'm going to use a 2-column proof to help me prove this. So I'm going to set it up by writing statement and reason. And I'm first just going to write down those 3 things that they give us, they're each given. So the first one is that triangle ABC is a right isosceles triangle. The next one is that AB is congruent to AC. The last one is that X is the midpoint of AC. So So we will end up using that. We could show that these are congruent to each other. But what I want to actually do is find the coordinates of x here. So I'm going to use the midpoint formula to help me do that, since I know the coordinates of the other 2 points. So here I get x is equal to, going to be 2a plus 0 divided by 2, and then 0 plus 2a divided by 2 for the y value. When we simplify that down, we just get the coordinates of a. So let's write that statement down in our proof and give the reason of the midpoint formula. And then I'll also mark that on my diagram, that point, the coordinates of AA. So now what I want to do is show that this line segment here, AX, is congruent to BX. And to do that, I'm going to use the distance formula. So that will be the square root of 0 minus a squared plus 2a minus a squared. So now we can simplify that to the square root of a squared plus a squared. Now simplify down to the square root of 2a squared. And then you can pull out that a squared out of there, so you get a times the square root of 2. So that is the length of AX. So now what we want to do is use the distance formula to find the length of BX. So we're going to use a minus 0 squared plus this a here minus 0 squared. And when we simplify that, we'll see that it also equals a times the square root of 2. So now we can say that AX is equal to BX by using the distance formula. We justified these 2 markings here. And then finally, we can say that triangle AXB is isosceles. And that's because of the definition of isosceles triangle. Now, one reason why I like this problem a lot is because each time we take the midpoint of the hypotenuse and connect it down to the vertex, we create another isosceles triangle. So if I was to go from here down to here, that creates another isosceles triangle where these 2 sides here are congruent to each other. Then if I was to do that again, midpoint, that creates another one where these 2 are congruent to each other. And now we can just keep doing that again and again and again. So it creates a smaller and smaller isosceles triangle, and they get infinitely small as we go down and down. So at this point, this line segment here is congruent to this one here. So small you can barely see it. Okay, so that's it for today. I do want to let you know I think the homework might be a little bit longer than usual, so just make sure you plan accordingly. And obviously ask any questions you have along the way.